There is a black hole at the center of our galaxy. It has been sitting there for 4 billion years. Quiet, patient, mostly ignored. Then one night in 2019, astronomers pointed a telescope at it, and something was wrong. It was glowing, brighter than anything ever recorded, 75 times more active than normal. And nobody, not a single person on Earth, knew why. The astronomers watching that night were at the Keck Observatory in Hawaii. Routine observation, nothing special scheduled. They had been pointing instruments at this exact spot for years, and then, in a single night, the data changed completely. The brightness spiked to twice the previous all-time record. They checked the instruments. They checked the data. Nothing was wrong with the telescope. Something was wrong with the black hole. To understand what this means, you need to understand the scale. Sagittarius A star, that is the official name, contains 4 million times the mass of our Sun. 4 million. If you replaced our Sun with it right now, the event horizon would stretch almost to the orbit of Mercury. Everything inside that boundary, gone. And this object sits 26,000 light-years from Earth. So what we saw in 2019 actually happened 26,000 years ago. We are watching ancient history in real time. A black hole does not actually suck things in like a vacuum cleaner. That is a myth. What it does is create an incredibly deep gravitational well. Gas and dust spiral toward it, forming a disk, called an accretion disk, that heats up to millions of degrees as material falls inward. That heat releases energy, light, X-rays, infrared radiation. When the accretion disk gets more material, it glows brighter. In 2019, something fed Sagittarius A an enormous amount of material all at once. The prime suspect is a gas cloud called G2. In 2014, it made an extremely close pass to Sagittarius A. Astronomers watched the whole thing live and predicted a spectacular feeding event. They prepared their instruments. They waited. And then almost nothing happened. The black hole barely reacted. G2 passed by and the universe seemed to shrug. Researchers were confused. Some called it a disappointment. But here is the thing about black holes. They do not always react immediately. Think of it like dropping a stone into a very deep well. You hear the splash immediately, but the ripples keep going for a long time after. When G2 passed Sagittarius A in 2014, it did not fall straight in. Gravity stretched and shredded parts of it. Those fragments went into highly elliptical orbits, and over the following years, they slowly spiraled inward. By 2019, 5 years later, the first significant chunks finally crossed the point of no return. The black hole had been waiting patiently for its delayed meal. The point of no return has a name: the event horizon. It is the boundary where the escape velocity, the speed you would need to travel to escape, exceeds the speed of light. Since nothing travels faster than light, nothing that crosses the event horizon ever comes back. Not gas, not dust, not information, not even the light itself. Once something crosses that line, the universe simply never hears from it again. In 2019, we watched material cross that line in enormous quantities. We saw the last light it would ever emit. But here is what makes the 2019 event even more unsettling. It was not the first time Sagittarius A behaved this way. There is evidence carved into the galaxy itself of something far more violent in the past. Above and below the center of the Milky Way, there are two enormous structures called the Fermi bubbles, discovered in 2010. Each one stretches 25,000 light-years away from the galactic center. Together, they span half the visible height of our galaxy. Those bubbles are made of high-energy gamma rays and fast-moving gas, and the only thing that could have created them is a massive outburst of energy from Sagittarius A itself. Somewhere between 1 and 3 million years ago, our black hole did not just flare, it erupted. It released so much energy in such a short time that it blasted two enormous cavities into the gas surrounding the entire galaxy. We are still seeing the aftermath today. The universe remembers even when we forget. And those galaxies are not unusual. They are actually the normal ones. Most large galaxies in the universe have an active supermassive black hole at their center. We call them quasars, or active galactic nuclei. They fire jets of plasma millions of light years into space. They outshine every single star in their galaxy combined. By the standards of the universe, our Sagittarius A is the unusual one. It is a sleeping giant in a cosmos full of giants that are very much awake. So why is Oz asleep? The answer probably comes down to food supply. Active black holes are in galaxies with abundant gas available to consume. The Milky Way has used up most of its easily accessible gas. Star formation in our galaxy has slowed dramatically compared to younger galaxies. Sagittarius A is not dormant because it is different. It is dormant because it has already eaten most of what was available. It is not sleeping. It is waiting. The best evidence we have about Sagittarius A comes not from watching the black hole itself, but from watching the stars around it. There is a star called S2 that orbits Sagittarius A once every 16 years. At its closest approach, it moves at nearly 3% the speed of light. 3%. That is 9,000 kilometers per second. Astronomers have tracked S2 through multiple complete orbits, and by measuring exactly how gravity bends its path, they have mapped the mass and location of Sagittarius A with extraordinary precision. In 2018, as S2 made its closest approach, astronomers detected something predicted by Einstein over 100 years ago: gravitational redshift. As light from S2 climbed out of the intense gravitational field of Sagittarius A, it lost energy. Its wavelength stretched, its color shifted slightly toward red. This is time dilation made visible. Time runs slower near massive objects. S2 experiences time differently than we do. Its clocks tick slower. Every time it swings close to the black hole, it ages a little less than it should. In 2019, the same year as the mysterious flare, humanity did something that should have been impossible. We photographed a black hole. Not Sagittarius A, a different one, M87 star. A supermassive black hole 6.5 billion times the mass of our Sun, sitting 55 million light-years away. The Event Horizon Telescope collaboration linked radio telescopes across the entire planet into one Earth-sized instrument. And what they captured was the shadow of the event horizon surrounded by glowing gas, a dark circle inside a ring of fire. 3 years later, in 2022, they did it again. This time they photographed Sagittarius A itself, our black hole. It was harder than M87 because Sagittarius A is smaller and its material orbits faster, meaning the image changes on timescales of minutes rather than hours. But they got it. A fuzzy orange ring with a dark center. The first direct visual evidence of the object that has sat at the center of our galaxy since before Earth existed. We finally saw it with our own eyes. What you see in that image is not the event horizon itself. The event horizon is completely dark. No light escapes. What you see is the photon ring, a region just outside the event horizon where light is bent so severely by gravity that photons orbit the black hole before either escaping or falling in. Some of that light has orbited multiple times before escaping toward our telescopes. When you look at that image, you are seeing light that is looped around the black hole before reaching your eyes. While we were building better images, another discovery was changing everything. In 2015, LIGO, the Laser Interferometer Gravitational Wave Observatory, detected ripples in space-time itself. Two black holes, 1.3 billion light-years away, had merged. The collision released more energy in a fraction of a second than all the stars in the observable universe emit in that same fraction of a second. And the ripple from that collision, traveling at the speed of light for 1.3 billion years, moved the LIGO detectors by less than 1,000th the diameter of a proton. We detected it anyway. The precision required to measure that is almost incomprehensible. The LIGO arms are 4 kilometers long. The mirrors at the ends are among the smoothest objects ever manufactured. The laser bounces between them 280 times before being measured, and the movement being detected is 10,000 times smaller than an atomic nucleus. We built a machine that can hear the universe move, and what we are hearing is black holes, merging, growing, feeding, all across the cosmos. There are not just 2 kinds of black holes: supermassive ones at the centers of galaxies and the small ones detected by LIGO. There is an entire population of black holes across the universe of different sizes formed through different processes. Stellar mass black holes form when massive stars collapse. They range from about 5 to 100 solar masses. Then there are intermediate mass black holes, theoretically between 100 and 100,000 solar masses, that we have almost never directly detected. And then the supermassive ones, millions to billions of solar masses. The missing middle is one of the biggest mysteries in astrophysics. Where did the supermassive ones come from? This is a genuine open problem. The universe is only 13.8 billion years old, but we have found quasars, actively feeding supermassive black holes, when the universe was less than 1 billion years old. There was not enough time for them to grow to that size through normal stellar collapse and merging. Either they formed through some exotic early universe process, or they grew much faster than our models allow, or both. The origin of supermassive black holes is unsolved. Now go to the other extreme. Go small and go strange. In 1974, Stephen Hawking made a prediction that shocked physics. Black holes are not actually black. They emit radiation, very slowly, almost undetectably slowly for large black holes, but they emit it. The mechanism involves quantum mechanics at the event horizon, where pairs of virtual particles pop into existence constantly. One falls in, the other escapes, and over time the black hole slowly loses mass. For a black hole, the mass of our Sun, this process would take 10 to the power of 67 years. The universe is only 10 to the power of 10 years old. We will never observe it for a large black hole. But it means that black holes are not eternal. And Hawking radiation created the deepest unsolved problem in theoretical physics: the information paradox. In quantum mechanics, information is never destroyed. Every state of every particle is encoded and preserved, even if scrambled beyond recovery. But if a black hole slowly evaporates through Hawking radiation, and that radiation is completely random, carrying no information about what fell in, then information is destroyed. Quantum mechanics and general relativity directly contradict each other. One of them must be wrong, or both are incomplete. We do not know which. Inside the event horizon, physics breaks down completely. Our equations stop working. General relativity predicts a singularity at the center, a point of infinite density where space-time curvature becomes infinite. But infinite means the math has failed. Physicists generally believe singularities are not real. They are a sign that our theory is missing something. What actually happens at the center of a black hole requires a theory of quantum gravity that we do not yet have. The center of a black hole is the most unknown place in the universe. If you fell into a large black hole, you would not notice crossing the event horizon. There is no wall, no visible boundary, just space. But as you fell deeper, the tidal forces, the difference in gravitational pull between your head and your feet, would grow until they overcame the molecular bonds holding your body together. You would be stretched into a thin stream of atoms along the direction of your fall. Physicists call this spaghettification. It is one of those terms that sounds almost funny until you think about what it actually means. We have actually watched this happen. Not to people, obviously. To stars. A tidal disruption event occurs when a star passes too close to a supermassive black hole and gets torn apart. Half the stellar material falls into the black hole. Half gets flung outward at enormous speeds. The infalling material heats up and glows, producing a flare that can briefly outshine the entire galaxy. We have detected dozens of these events. They are beautiful and catastrophic simultaneously. Some black holes do something even more dramatic. They launch jets. Narrow beams of plasma and radiation fired from the poles of the black hole at nearly the speed of light. These jets can extend for millions of light years, longer than the distance between galaxies. The mechanism is driven by magnetic fields threading through the accretion disk and twisted by the rotation of the black hole into a structure that accelerates material outward. The most energetic jets in the universe carry more power than 1 trillion suns combined. Black holes can spin, and spinning changes everything. A non-spinning black hole is described by a single number, its mass. A spinning black hole is more complex. It drags space-time around with it like a whirlpool. This effect is called frame dragging. Near a maximally spinning black hole, space-time itself rotates. You cannot stay still even if you wanted to. The universe itself is being stirred. And the spin of a black hole determines how efficiently it can convert infalling matter into energy. A maximally spinning black hole can convert up to 42% of infalling mass into energy. Our most efficient nuclear reactions convert less than 1%. Here is something genuinely strange. The mass of a supermassive black hole and the mass of the galaxy around it are correlated. Not loosely, tightly. Across thousands of galaxies of completely different sizes and types, the ratio holds. The black hole is always roughly the same fraction of the total galactic mass. How does the black hole, sitting in the tiny, dense core of a galaxy, know how big the galaxy around it is? They cannot directly communicate across those distances, yet somehow they grew together, regulated each other. The black hole and the galaxy evolved as a single system. The mechanism is feedback. When a black hole feeds aggressively, it launches jets and winds that heat and blow away the gas in the surrounding galaxy. No gas means no new stars can form. The galaxy stops growing. And as the gas is expelled, the black hole runs out of fuel and goes quiet. The galaxy cools. Gas slowly falls back in. The black hole wakes up again, feeds, blows out the gas again. It is a cycle. The black hole regulates its own galaxy like a thermostat regulates a room. Sagittarius A has done this to the Milky Way, multiple times. The Fermi bubbles are the receipts. Now look forward. In approximately 4.5 billion years, the Milky Way and the Andromeda galaxy will collide. Not a gentle brush, a full merger. Over hundreds of millions of years, the two galaxies will pass through each other. Stars will be flung into new orbits. Gas clouds will collide and trigger massive bursts of star formation. And the two supermassive black holes at the center of each galaxy will begin their long, slow spiral toward each other. When two supermassive black holes merge, the process takes millions of years. First, they orbit each other, gradually losing energy to gravitational radiation, spiraling closer, faster. The final merger, the last few orbits, would release gravitational waves powerful enough to distort spacetime across the entire local universe. Every gravitational wave detector on Earth would scream simultaneously. The signal would be unlike anything we have ever measured. Sagittarius A and the Andromeda black hole will produce it in about 6 billion years. Nobody alive today will see it, but the physics is already determined. In 2023, multiple pulsar timing array collaborations announced something remarkable. They had detected the gravitational wave background, a constant low hum of gravitational waves filling the entire universe. Not from a single merger, but from millions of supermassive black hole mergers happening across the cosmos simultaneously. By using pulsars, the most precise natural clocks in the universe, as a galaxy-sized gravitational wave detector, they found that space-time itself is vibrating. Right now, at frequencies too low for LIGO to detect, the universe is buzzing with black hole activity that we are only beginning to hear. Some physicists have proposed something even more unsettling. What if dark matter, the invisible substance that makes up 27% of the universe's mass energy, is actually primordial black holes? Black holes formed in the first fraction of a second after the Big Bang, before any stars existed. The idea has been proposed and challenged and partially revived multiple times. Current observations rule out most of the mass range, but a small window remains open. We cannot completely rule out that the invisible scaffolding holding galaxies together is made of ancient black holes, smaller than asteroids, scattered throughout the cosmos. Back to the information paradox, because it gets stranger. In 2012, 4 physicists published what became known as the firewall paradox. They showed that the 3 most fundamental principles of physics, general relativity, quantum mechanics, and the no-cloning theorem, cannot all be simultaneously true at the event horizon. If you try to preserve all 3, you predict that the event horizon is not empty, peaceful space, but a wall of high-energy radiation that would instantly destroy anything crossing it. A firewall. Either falling into a black hole is instantly fatal, or one of our most trusted theories is wrong. We do not know which. The information paradox led to something even more radical: the holographic principle. The idea that all the information describing a 3-dimensional volume of space is encoded on its 2-dimensional boundary, like a hologram. For a black hole, this means all the information about everything that has ever fallen in is somehow encoded on the event horizon surface, not inside, on the surface. This is not metaphor. This is a mathematical result that has survived decades of scrutiny. If it is correct, then the 3-dimensional interior of a black hole is in some sense a projection from its 2-dimensional boundary. And if it applies to black holes, it may apply to the entire universe. We may all be living in a projection. In 2013, Juan Maldacena and Leonard Susskind proposed something that sounds like science fiction. They called it ER equals EPR, Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen pairs, quantum entangled particles, might be the same thing. Entangled particles may be connected by microscopic wormholes through space-time. And if this is correct, then the inside of a black hole and the outside are connected not by crossing the event horizon, but by quantum entanglement woven through the fabric of space-time. The geometry of space itself may be built from quantum information. We are not sure. But the math works. We cannot directly observe Hawking radiation from real black holes. It is far too faint. But in 2019, a physicist named Jeff Steinhauer created a sonic black hole in a laboratory. A flowing fluid moving faster than the speed of sound in that fluid, so phonons, sound waves, cannot escape, just like light cannot escape a real black hole. And in that sonic black hole, he detected the acoustic equivalent of Hawking radiation. Thermal phonon pairs produced at the sonic horizon. It is not a real black hole, but it behaves like one. And the Hawking radiation was there exactly as predicted. The next generation of instruments will transform what we know. The next generation Event Horizon Telescope will produce black hole images sharp enough to watch material orbiting in real time. The Laser Interferometer Space Antenna, LISA, scheduled for the 2030s, will detect gravitational waves at the low frequencies produced by supermassive black hole mergers across the universe. The Einstein telescope will be 10 times more sensitive than LIGO. Every one of these instruments will tell us things about black holes that we currently can only theorize about. What about Sagittarius A specifically? Will it flare again? The honest answer is, we do not know. There are more gas clouds in orbits that will bring them close to the galactic center in the coming centuries. The star S2 will make another close pass. The environment around Sagittarius A is not static. It is a dynamic region with material constantly moving through it. The 2019 event may have been unusual, or it may be a sign that Sagittarius A is entering a slightly more active phase. We would need centuries of observation to be sure. We have had modern instruments pointed at it for decades. There is one more mystery near Sagittarius A that nobody has fully explained. In the region immediately surrounding the black hole, where the tidal forces are so extreme that gas clouds should be torn apart before they can collapse into stars, there are young stars. Massive young stars that should not exist there. They are called the S stars, and they orbit Sagittarius A in tight elliptical paths. How they formed in such a hostile environment is unknown. One idea is that they formed further out and were somehow transported inward. Another is that the environment near black holes permits star formation through mechanisms we do not yet understand. Now project far forward. Not billions of years, trillions. In about 100 trillion years, the last stars will burn out. The universe will enter what cosmologists call the degenerate era. White dwarfs, neutron stars, cold dark matter, no new light. Then the black hole era, lasting from 10 to the 40th to 10 to the 100th years. In this era, black holes are the most significant structures in the universe. They continue to slowly evaporate through Hawking radiation. The largest ones, the supermassive black holes at the centers of merged galaxies, will be the last objects to exist. And eventually, they too will finish evaporating. The last particles of Hawking radiation will disperse, and the universe will contain nothing but cold photons and a quantum vacuum. The void wins, not as an exception, as the final state of everything. But even that void is not truly empty. Quantum mechanics forbids true emptiness. Virtual particle pairs flicker in and out of existence at every point in space at all times. The vacuum seethes with energy, and that vacuum energy, the zero-point energy of empty space, is almost certainly connected to dark energy, the force driving the accelerating expansion of the universe. The predicted value from quantum field theory and the measured value from cosmological observations differ by a factor of 10 to the power of 120. The largest discrepancy between theory and measurement in the history of science. The void is literally where our best understanding of physics collapses. Come back to the beginning, to that night in 2019, to astronomers in Hawaii watching data that should not exist. On a clear, dark night, you can see the center of the Milky Way with your own eyes, a dense band of stars in the direction of the constellation Sagittarius. Somewhere in the middle of that glow, right now, Sagittarius A sits, waiting, perhaps feeding on something, perhaps quiet. We cannot tell from here. We are 26,000 light-years away, and the light telling us what is happening right now will not arrive for another 26,000 years. What we know about black holes would have seemed like magic 100 years ago. We have photographed them, heard them merge, mapped the orbits of stars around them, watched them tear stars apart, built laboratory analogs of their quantum behavior, and every answer has produced 3 new questions. The information paradox, the firewall, the interior singularity, the origin of the supermassive ones, the nature of dark matter, the discrepancy in vacuum energy. These are not loose ends, they are the frontier, the places where our understanding of the universe stops and the unknown begins. In 2019, a black hole 26,000 light-years away did something unexpected. We do not know exactly why, We have theories, good ones, but not certainty. And that uncertainty is not a failure of science. It is science working exactly as it should. Every time we look at Sagittarius A, we are looking at the edge of what we understand. The black hole at the center of our galaxy is not just an object, it is a question. And the question is getting more interesting the longer we look. End of script. Total blocks, 72. Estimated voiceover duration, 38 to 42 minutes at 130 words per minute.